So we will start with the week 3 tutorial session. So this time I think you must have seen the lectures for the turbojet engine cycle, the TS diagrams. Is that right? Okay. So we'll just have a quick revision over here. This is a diagram for the turbojet engine, and we've been through this before, so I've just numbered the different stations. You have an inlet over here at station 1, and then between station 1 and 2 you have the diffuser, so you can see the area is increasing, and then between 2 and 3 you have the compressor. The compressor is attached to the turbine through a shaft, and between the compressor and the turbine you have this combustion chamber. Okay, so the station numbers are clear, I hope. After the turbine we have an afterburner, so sometimes the afterburner is used, sometimes it is not used. Okay, and then finally you have the nozzle and then the exit. Okay, so the TS diagram must be familiar to you. So here I have drawn the ideal TS diagram, and you can see in the ideal case, when you're going from station 1 to 2, that is in the diffuser, your temperature increases isentropically. Then from 2 to 3 also there is an isentropic increase, but the difference here, what is the difference between station 2 and station 3? We have a compressor, right? So what is the difference between a diffuser and a compressor? Both are compressing air. What is the difference? Answer? Hello, I'm audible? Yeah, someone please answer, guys. Can you all hear me? Yeah, give me an answer. Come on. What is the difference between a diffuser and a compressor? So simple. Okay, what do you mean by passive and active? Okay, so you're saying for compressor we need to provide work to run it, and the other way of looking at it is that diffuser does not have any moving parts. A compressor has moving parts. It rotates the incoming fluid. It is doing work on the fluid, right? So in diffuser we are not providing any work, but in compressor we are providing work to the fluid. So when you go from 1 to 2, that is across a diffuser, your static pressure changes but the stagnation pressure remains same. So last tutorial, if you have seen the last tutorial session, we drew how stagnation pressure changes along the axis of a turbojet combustor, a turbojet engine, and also how the stagnation temperature changes. So I hope you remember that. Just go and review that once more. So here from 2 to 3 we have some work input, okay, and from 3 to 4 we have heat input. From 4 to 5 we have work output, which is your turbine is going to give out some work. And then if you do not have any afterburner, then the fluid is simply going to exhaust through the nozzle. So is this clear? Yeah, so this is ideal. Now we'll draw what happens in the real case. So in the real case, when the fluid moves through the diffuser or through the compressor, the flow is not isentropic. We have assumed it is isentropic, but it actually follows some non-isentropic path, like you can see here. So this is too real. Okay, and then further there will be another non-isentropic path, and then because you are adding some same amount of heat, then the temperatures achieved will be even higher. And you should note that the just sorry. So you should note over here that uh, during the heat addition, the pressure is not going to remain constant in the real case, but we assume that it remains constant. Okay, so this is going to go along some other path, just like this, and then it will follow again a non-isentropic path during expansion, and then finally another non-isentropic path. So you see there's a lot of difference between the ideal cycle and the real cycle. So is this difference clear? Yeah, so similarly you should try the ideal versus the real cycle for an afterburner. And now the difference here you can see is when you switch on the afterburner, it is going to add more heat. So first your fluid went through the diffuser, compressor, then in the combustion chamber heat was added, so some fuel was burned, and then it was expanded through the turbine. But before having any exhaust through the nozzle, you switched on the burner and added more fuel over here. So there is a secondary heat input, and that raises the temperature even higher. So what is worth marking here is that the temperature increase is going to be very high. So the temperature that you reach in the combustion chamber, that was let's say that was TCC, and then the temperature that you reach after going through the afterburner, say that is TAB. The aim of using the afterburner is to raise the temperature very high, so it will be true that TAB is more than TCC. Okay, now the question here is how much heat do you need to add in? So will Q2 dot be more than or less than Q1 dot? So will you have to add a lot of heat? See, initially you were bringing the fluid from a temperature of T3 to T4, right? So my question is, how much fuel do you need to add to get it from T3 to T4 compared to getting the fluid from T5 to T6 using the afterburner? Where will you need more fuel? You're saying in T3 to T4. Okay, what is the reason? Yeah, but then in afterburner our aim is also to reach much higher temperatures, right? That is right, but it is high temperature already. So you're saying anyways T5 would be approximately more than T3. But see, there is one difference. In the combustion chamber, the pressures at which you operate, this P3 equals P4, this pressure is much higher. Okay, so in the combustion chamber you are operating at higher pressures, but in after expansion through the turbine, the pressure reduces. So in the afterburner, the operating pressure is lower, and when your fluid is at lower pressure, then for raising the fluid for the same amount of temperature you need more fuel. So even if the delta T is same in combustion chamber and in afterburner, you will need more fuel in the afterburner because you are adding heat at lower pressures in afterburner. Is this clear? Okay, so last time I asked this question, why do we need to inject water methanol injection? And one of you also answered that it is a method of thrust augmentation, right? So this is a method of thrust augmentation. What does thrust augmentation mean? That your turbojet engine is designed to provide a certain amount of thrust at certain operating conditions, but then you want to improve its performance. So how can you improve its performance? One method is you switch on the afterburner. So then that adds more heat, raises the fluid to higher temperature, then the exhaust can be for a longer temperature difference, and as a result you will get more thrust. But then there is another method, that is you can inject water and methanol, and when you inject this mixture in compressor it has a certain effect, and if you inject it in combustion chamber it has some other effect, but in both the cases you increase the thrust. So my question was, why or how this water methanol injection is going to increase the thrust. So did you guys think about it? What could be the reason? Anyone? Any answers? Okay. No, but compressor already it is at lower temperatures. So if you even if you reduce the temperature, how is that going to help? So you are saying that, okay, if I add some water and methanol, see, first of all, if you remember, sorry. So if you remember that thrust equation went like thrust is m dot into ue minus u. So either you increase the exhaust velocity ue or you increase m dot. So one answer is that when you inject water and methanol you are increasing m dot. Okay, so then thrust should increase. Another thing is methanol can be used as a fuel in the combustion chamber, so that will also increase the heat addition. It will act like a fuel, so that will also help you raise the temperature in the combustion chamber, and it will increase the thrust. Now what happens otherwise in the compressor? You were right, the temperature is reduced because of water methanol injection. And why do we want to reduce the temperature? So like we discussed, there is difference between the ideal and the real cycle. So what is drawn here in light gray is the ideal cycle, and what you can see in dark gray, that is the real cycle. Okay, now if you do water methanol injection in the compressor, so what it will do, it will reduce the temperature. So you are at this condition, that is 3 real, okay, and then you inject water and methanol and bring down the temperature, whereas the pressure remains almost the same. Okay, so now you are going almost isentropically. So you have converted your compressor's behavior from non-isentropic to almost isentropic. But remember that the work you were extracting from this point up to this point, that was say 2 real to 3 real, that work was being extracted from the turbine. And when you inject water and methanol, the amount of work which turbine is doing will not reduce, it is not going to change. So the work from turbine is still the same. Okay, but what about the work from compressor? Earlier you were going from 2 real to 3 real, but now you are going from 2r to, you are going to say this 3 prime. Okay, now the work that your compressor needs is actually lesser. So what will happen if the turbine is providing more work than what the compressor needs? It will raise the pressure. So now you will go to higher pressures, and the moment you go to higher pressures, then for the same amount of fuel added, you will also reach higher temperatures. Does that make sense? So you have increased the thrust, you have increased the pressure that the compressor can achieve, and you have increased the maximum temperature that can be reached in your combustion chamber. So then your thrust will also increase. Is this clear? Hello, am I audible? Yeah, okay. So this was, if you add, this is case A, where when you add water methanol injected into the compressor, then you reduce the temperature, the work from the turbine remains same, work of the compressor has reduced. So when it takes the same amount of work from turbine, then it will compress the fluid to higher pressures. As a result, you will achieve higher temperatures, and finally your thrust will increase. But now what happens if we do this process in the combustion chamber? So let us say that I add water and methanol, I inject it into the combustion chamber. So usually your combustion chamber works in a condition such that when the fluid is going from your combustion chamber to the turbine, so this flow is almost choked. So the inlet of the turbine is like almost choked. So even if you keep adding a lot of m dot, that is whether you add water, methanol, or you add more fuel or more air, that is not going to affect the flow downstream. So you know the condition, you know what is a choked condition? Have you heard this word before? Choked condition. Yeah. So what is choked? Mac is approximately, yeah, it is approximately equal to 1. And then whatever changes you make in the upstream condition will not reflect in the downstream condition. So what happens now, you have started adding water and methanol into the combustion chamber, m dot is increasing, but the outlet of the combustion chamber is choked. So now what will happen, pressure will start building, right? So pressure in the combustion chamber will increase, and as a result, again you have high pressure and higher temperatures achieved in the combustion chamber, and again your thrust will increase. Okay, so these are the two cases of water methanol injection. So you should be able to explain it with this TS diagram easily. Okay, so now you guys have to help me out with these definitions because they have been discussed in the lectures, and I hope you have watched the lectures. So we'll discuss the efficiency of each component. So it's efficiency of the diffuser. So like we discussed, first, in an ideal situation, in a diffuser, the fluid should be compressed in an isentropic manner, right? So ideally you would go from state 1 to state 2 along this straight path. Okay, and expected is that you will achieve a pressure of this P2 expected, but in reality the pressure achieved will be lesser. So you will achieve lesser pressure and it will be on a non-isentropic path. So what we do is we assume that if the pressure ratio was same, so actually you have achieved this P2 achieved, right? So this P2 we will assume is equal to some P2S, which is a pressure you would have reached along an isentropic path. So we don't consider the initial expected pressure, we consider the same pressure which you have achieved, and for that pressure ratio, so P2 by P1 is equal to P2S by P1, and for this same pressure ratio we compare the temperatures, and that gives us the efficiency. So how do we define the diffuser efficiency? What is the formula here in terms of the temperature? Has this been discussed in the lectures? Have you watched the lectures? Yeah, just please answer me. I can hear only one voice. Everyone please participate in this. Okay, so I guess you're saying the same thing. T0 2S minus T1 divided by T0 2 minus T1. Okay, so here 1 is the common state between them, right? And always remember, efficiency can never be more than 1. Efficiency has to be less than 1. So here in a diffuser, what is happening? The kinetic energy is decreasing, and the ideal decrease should have been lesser. So you can also see from the diagram that this difference in the temperatures is lesser as compared to the difference between 2 and 1. So that is what we have written, that there is a difference between 2s and 1 state, which is in the numerator because it is smaller, and difference between 2 and 1 state is larger, so it is in the denominator. That is the way to remember. And ideally we would expect that the kinetic energy decrease is less, but actually more kinetic energy decrease is achieved in the diffuser. So the definition is that there is ideal kinetic energy decrease divided by actual kinetic energy decrease. Okay. Now similarly we can define the efficiency of a compressor. So in a compressor, again you are going from state 2 to state 3 non-isentropically, but you should have ideally gone in an isentropic path. So this is 2, this is 3, and this is a 3s state. So what is the efficiency formula? Okay, T naught 3s minus T naught 2 divided by T naught 2s, T naught 3 minus T naught 2, this. Okay, so this is, what is this? How does this formula come? What is a compressor doing? It is adding work, right? So ideally, to achieve the same pressure ratio, ideally you should have required lesser work, but in reality you will require more work. So here the definition will be ideal work in divided by real work in. Okay. And so for turbine it will be just the opposite, because in turbine ideally you would have to give lesser work, but in reality you have to perform more, right? So here it will be real work out divided by ideal work out. So now what is the definition in terms of the temperatures? So you are going from state 4 to state 5 in a non-isentropic path, but ideally you should have gone in an isentropic path like this. So this is 5s state and this is the state 5. So now what is the formula? Minus, okay, you're right, but it would be better if we write T naught 4 minus T naught 5, isn't it? Because 4 is the higher temperature. Okay, so T naught 4 minus T naught 5 divided by T naught 4s minus T naught 5. And you can easily remember these definitions by seeing the diagram. Just simply draw the diagram and see which one is the state where the temperature difference is more. That will come in your denominator. So here, okay, this is 4 is supposed to be the same state. So 4 is common, 5 is changing, right? So it should be T naught 4 minus T naught 5 divided by T naught 4 minus T naught 5s. And this denominator is larger than the numerator. That's it. Okay, and similarly in the nozzle. So in nozzle you will have, you're increasing the kinetic energy, but the real kinetic energy increase is going to be lesser as compared to what is expected in the ideal case, right? Okay, now what is the efficiency of nozzle in terms of the temperature? So here it is T naught 5 minus TE divided by T naught 5 minus TES. Okay. Then we have one last definition, which is the burner efficiency. So this is the efficiency of the combustion chamber where you are burning the fuel. So what happens is, say you actually give some m dot f, give some amount of fuel, but complete fuel is not going to undergo combustion. So then we define the burner efficiency as m dot f, which is actually burnt, divided by m dot f, which was given. So in an ideal situation, whatever is given to the combustion chamber, it will be burned. But in reality, lesser amount is going to be burned. So that is the burner efficiency. Okay, so now we'll just move on to the questions for this session. And I hope you all will help me out with the answers quickly because these are easy questions. Okay, so question number 1, efficiency of an ideal Brayton cycle. What happens? Does it increase with the compressor pressure ratio or decrease, or first increase then decrease? So what is the answer here? Yes, it increases with increasing pressure ratio. Okay, so this is the diagram. This is for turbojet. Now if I just ask you for turbo fan, where should it be? Should it be below turbojet or above turbojet? Turbo fan efficiency is more than or less than turbojet? Right. Okay, so that is for turbo fan. So next question, the pressure ratio of gas turbine power plant cycle operating with air. So they have given its air corresponding to maximum work for a given temperature limit of 305 Kelvin to 1020 Kelvin. So they have given T minimum. T minimum is equal to 305 Kelvin, and they have also given T maximum, which is equal to 1020 Kelvin. So what is the pressure ratio going to be? So what is the formula? What do we need to use here? So remember, for an ideal case, for an ideal gas turbine cycle or ideal Brayton cycle, what is the pressure ratio defined as? This is 1, 2, 3, 4. What is minimum temperature? Minimum temperature is at state 1, right? And maximum temperature is at state 3. And the pressure ratio is P2 by P1. So this is what is asked. So what is the formula here? P2 by P1 is equal to, so okay, in case you don't know these formulae, please refer to the lectures. Gamma by gamma minus 1. This is right, T2 by T1 to the power gamma by gamma minus 1. But we are not given T2 at all. We are given T3 by T1. So now what is the relation? Sorry, I didn't get you. Okay. T2 is equal to T3 into T1 under root. This is what you are saying. Is it? Is this right? Okay. So we can just combine all this and we can write the formula that we can write the formula here as P2 by P1 is equal to T3 by T1 to the power gamma by 2 into gamma minus 1. Okay, and then if you just put the values, that is 1020 divided by 305 to the power, what is gamma for air? It is 1.4. So 1.4 divided by 2 into 0.4. So if you evaluate this, you will get the answer. You want to do it? The answer is 8. Okay, approximately 8. Okay, so we'll move on to the next question. In an ideal open Brayton cycle consisting of only compressor, combustion chamber and turbine, that is basically the cycle we drew here, optimum pressure ratio is achieved when? So just see the options and give me an answer. what is the ideal situation? They're talking about compressor exit temperature, which is state 2 over here, and then the other thing they are comparing is the turbine exit temperature, that is 4. So what is the ideal situation? So I cannot hear you. Please speak clearly. Yeah, both should be equal. Okay, why? Right, so the work extracted from the turbine should be equal to the work that the compressor needs. So now what happens if say this, let us just assume that T4 was much lower, say you were letting it exhaust till lower temperatures, then the work given by turbine is much more, isn't it? And you're not utilizing that much in the compressor, so some extra work is being produced which is going waste. So the most optimum situation would be when T2 is equal to T4. Okay, so that's the answer in this case. Okay, next question. If beta is the maximum to minimum temperature ratio, which we just wrote earlier, which is beta is equal to T3 by T1 from that cycle, then the work ratio of gas turbine power cycle for a given gas and fixed pressure ratio increases or decreases with beta. So what is the answer here? A similar question that I have come up with is, what happens if you increase the compressor pressure ratio? Will the net work produced by the cycle increase or decrease? So let's first answer the question which is in blue. So if you increase this beta, that is T3 by T1, that ratio increases. Yeah, someone was saying something? Okay, what is work ratio? You know what is work ratio? It is work done by turbine divided by work done by compressor. Yeah, it increases with increase in beta. Okay, so the answer is this one. Now what you can just draw the diagram and see this. So I have drawn 3 situations here. What you can see in the golden this golden flow chart, that is when the compressor pressure ratio is very high. So 1 to 2, see, you can see that the pressure ratio is very high. Then there is this red diagram, that is the red state, that is when the compressor pressure ratio reduces a little bit, and then the green state where you reduce the compressor pressure ratio even more. So as we basically increase the compressor pressure ratio from this states A to B to C, you can see that the net work done is actually the area enclosed in this cycle, isn't it? And the area will initially increase. So the area of the red shaded region is more than the area of the green shaded region. But then if you further increase the compressor pressure ratio, then the area decreases. So from this diagram, is it clear that the net work done by the cycle, it will first increase up to some optimum, and then it will decrease as you increase the compressor pressure ratio. Is this clear? Okay. So we have seen 2 effects right now here. We have seen how the net work of the cycle changes when you change the maximum to minimum temperature ratio, and also what happens if you change the compressor pressure ratio. How does the net work of the cycle change? Okay, so then the next question is a numerical question. In a gas turbine power plant, the inlet conditions are given. So the inlet pressure is given, inlet temperature is given, and also an inlet volume flow rate of 7 meter cube per second is given. And they've given the cycle pressure ratio. So what is cycle pressure ratio here? So I have drawn the cycle in the TS diagram. So what is cycle pressure ratio? Is it P2? Yeah. Okay, there are many questions to go. Please answer me quick. What is cycle pressure ratio? Is it P2 by P1 or is it P3 by P2 or P3 by P1? What is cycle pressure ratio? Is it P3 by P1? No, it is P2 by P1. Cycle pressure ratio we discussed right now. See, beta is the maximum to minimum temperature. But then we discussed how this T3 by T1 is related to P2 by P1. And P2 by P1 is the cycle pressure ratio because or compressor pressure ratio. That is what defines the working of a turbojet engine. Okay, so we always refer to this P2 by P1 as the cycle pressure ratio. Okay, so first you should be clear what is given in the question and then you should solve it. So now we know P1. P1 is given as 120 kilopascals. Okay, then T1 is given as 310 Kelvin, and then a volume flow rate is given as 7 meter cube per second. And then this pressure ratio, which is RP, which is equal to P2 by P1, is given as 7. Now what they are, and they have also given turbine inlet temperature. What is turbine inlet temperature? Is it T2, T3, T4? What is it? Yeah, T3. So T3 is given as 1023 Kelvin. Okay. Now find out the thermal efficiency, net work output and work ratio. So I have written down the formulae that we are going to use. Again, derivations, please refer the lectures. If you have any doubts, you can ask me and we can discuss the derivations also. Okay, so I'll just go ahead and give you these solutions. So thermal efficiency can be found. See, remember what is thermal efficiency definition? How much change in kinetic energy is brought about for a certain input amount of energy due to burning of the fuel, right? So using this definition, and then you can write the change in the kinetic energy in terms of the stagnation enthalpies, that is H02 minus H01, H03 minus H04. That change in kinetic energy you can find out, right? So it will be H03 minus H04 minus H02 minus H01 divided by what is the energy added due to burning of fuel, that is along 2 to 3. So here you can write it as H03 minus H02. So using this definition you can, and using some gas dynamic relations, you can derive the formula that thermal efficiency is equal to 1 minus 1 divided by the pressure ratio to the power gamma minus 1 divided by gamma. Okay. Now if you just plug in the values, gamma is for air 1.4, RP is given as 7, thermal efficiency will turn out to be 43%. Okay, so I'll just move on to the next part of the question, which is the net work output. So net work output is the work output by turbine minus the work input to the compressor. So how do you calculate now the work produced or consumed in this case? How will you calculate work turbine and work compressor? CP delta T. Okay, so we know this is CP. Going back to the cycle, for turbine it should be T04 minus T03, and for the compressor it will be CP times T02 minus T01. Now what all information do we have? Do we have T04, T03? Do we have all these values? How will we find them? T03 and T01, and we need to find T04 and T02. So 1 to 4 we have the compressor pressure ratio, so we can use the adiabatic relations and find. What about 3 to 4? Do we have the compressor pressure ratio? Do we have the compressor pressure ratio? So in an ideal gas turbine power plant, or in an ideal Brayton cycle, what is the pressure ratio for a turbine? So going back to this diagram, okay, and going back to question 3. In the ideal situation, what happens is, so you are operating between this pressure, say PB, and say this is pressure PA. So what is the compressor pressure ratio? It is PB by PA. And then what is the pressure ratio across the turbine? It is PA by PB, right? So it's just 1 by the cycle pressure ratio. Is that clear? Did you understand this? Okay, so maybe I'll just redraw here. So in a Brayton cycle, how do we define we draw these isobaric lines, right? So let us say this is pressure A, and then you have this another isobaric line which is PB. Okay, so you're going in a compressor from state 1 to state 2, so you are increasing the pressure from A to B, and then there is isobaric combustion from 2 to 3, and then from 3 to 4. So okay, ideal situation, we also want this temperature to remain same, so then the combustion will go all the way up till here and then come down like this, but the pressure ratio will remain same. Okay, I haven't drawn the pressure lines correctly, so this is PA. Did you understand, or should I redraw? Understood? Okay, so the pressure ratios across the compressor and turbine remain same, and temperature, that is T2 and T4, will remain same. Okay, so PA by PB is equal to the compressor pressure ratio, and it is 1 by turbine pressure ratio. Okay, and T2 is equal to T4. So this is the case for ideal Brayton cycle. Okay, so using this, now we can find out all the information that we need. So let us start here. We know T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So can you calculate and tell me what is T2? So we are using gamma as 1.4 for air over here. Okay. And quickly tell me the answer. Okay, it's approximately 540 Kelvin. And then you can calculate T4. So what is T4? T4 by T3 is equal to P4 by P3 to the power, again, gamma minus 1 by gamma. But what is P4 by P3? P4 by P3 is nothing but P1 by P2 to the power gamma minus 1 by gamma. So from this, calculate T4 and tell, because T3 we know. Go back and display the question for you. So T3 is known to us as 1023 Kelvin, right? So what is T4 going to be? Yeah, okay, 587.5 Kelvin is the answer I have here. Okay, so now we have T2, we have T4. So what is work of compressor? It is m dot Cp into T2 T2 minus T1, which is equal to, so Cp, see the values are given over here in the question. Cp is also given, the gamma is also given, and R value is also given. Okay. So you can calculate the work of the compressor. I'll just write the answer over here. It is 2179.87 kilowatts. If you have any doubts in the steps how to calculate this, please ask me. Work of the turbine is again m dot Cp into T3 minus T4, which is equal to 4131.39 kilowatts. Okay. Any doubts over here? Okay. So then you can find the net work also. That's easy. W net is simply the difference between them, and that turns out to be 1951.52 kilowatts. And then there was another question which asked what is the work ratio. So work ratio is defined as the compressor work divided by the turbine work. So that again you can find what is Wc by Wt. So that turns out to be about 0.53. Okay, so should I move on to the next question? Okay, so the next question is on a real gas turbine plant, that is we'll be dealing with non-isentropic paths. So a simple gas turbine plant takes air at 1.2 bar. So we are given P1. Okay, P1 is equal to 1.2 bar, and then 25 degrees Celsius. So that is the inlet temperature T1. You can write it in kelvins, which is 298 Kelvin. And then it compresses it to a pressure of 4 bar. So if, oh I didn't write this, 298 Kelvin, and then P2 is known to be 4 bar. So you also know the compressor pressure ratio. And the efficiency of the compressor, remember we defined eta C. So eta C is given to be 0.88. But what was eta C? Definition, it was T naught 2S minus T1 divided by T naught 2 minus T1. So we know this is 0.88. So from here we can find T naught 2 and T naught 2S. Okay. So if you know P2 by P1, this to the power gamma minus 1 by gamma, this will give me what? What is the right hand side supposed to be? Is it T2 by T1 or is it T2S by T1? T naught 2S, right? Because this relation is valid only for adiabatic conditions, and we are going for state 2 we are going from a non-isentropic path. Okay, so alright, so from here we can get T naught 2S. So calculate and tell me what is T naught 2S. No, that's not what I have. So the compressor pressure ratio is 4, isn't it? So gamma, they have given gamma is also 1.4. Right. Yeah, so here there's a mistake here. mistake in the solution, so I'll probably have to change the question then. Let this be 1 bar, because otherwise all the other subsequent answers will become wrong. Yeah, 443 Kelvin approximately, right? So T02S is 443 Kelvin. So now using this eta C definition, we can find what is T02. What would that be? Yeah, so I'll write approximately 463 Kelvin. Okay. Okay. Now what does the question say? So then the air passes to the combustion chamber, and after the combustion, the gases enter into the turbine at a temperature of 1210 Kelvin. So what we are given now is T03. T03 is given to us as 1210 Kelvin. Now expansion of these gases take place to 1.2 bar pressure. Again, let me see what pressure they have used. Okay, anyways, let us calculate. And then if the isentropic efficiency of the turbine is given to be 82%, then you have to find the actual temperature of the exit of the compressor and turbine, which we have already done. Heat rejection by the plant is, and the work ratio is, and the thermal efficiency. So basically you have to solve the entire cycle, and then you can find all these questions. So eta nozzle is equal to 0.82. And what is the definition in terms of temperature? Definition in terms of temperature for nozzle? Oh, it's not nozzle, it's turbine. Sorry. Yeah, T04 minus T03 divided by T04S minus T03. Oh, it should be upward, but that's fine. Okay, so now we can calculate T04S because we know the pressure ratio. So P4 by P3 to the power gamma minus 1 by gamma, that will be equal to T04S by T03. So calculate T04S and tell me. Yeah, it's 814 kelvins. Okay. Yeah, so if you just plug this back here, and you also know T03 and you know the turbine efficiency, using that you can get T04 is equal to 886 kelvins. Is it? Yeah, okay. Okay, so now we have to calculate. Now we know all the temperatures and pressures. So question 8 was to calculate the temperature, actual temperature. So what is actual temperature? It is not the S condition. So if you have calculated T02S, that is the ideal temperature. Actual temperature is T02. So this is the answer for the actual compressor outlet temperature, T02, and actual turbine outlet temperature, which is T04. So this is the answer. Okay, and then question 9 is heat rejection by the plant. So what is heat rejection by the plant? Yeah, so Q out, that would be equal to, so go back to the cycle. So here you have certain initial temperature, which is T1, and then the final temperature after the entire cycle is over, that is T4. So this is the final change in temperature. So the final outlet heat is going to be Cp into T4 minus T1. So if you know all these values, so this is T04 minus T01 actually. So if you just plug in all the values, and the value of Cp is also given. So this is going to be 590 kilojoule per kg. Okay. Then the next part is the work ratio. So now work ratio, again, that was work ratio is WC by WT. Okay, and also you have to find the net work done. So work net is equal to WT minus WC. So that you can calculate as Cp delta T naught for turbine minus Cp delta T naught for compressor. So what is net work? Please calculate and tell me. Oh, I could not hear that. No, that's not what I have. So Cp value, what have you used? Cp value is 1.005 kilojoule per kg Kelvin. Anyone else? Is everyone else calculating? Are you getting the answers? So just maybe I should move this to the center. No, it's not. No, it's not so high. Maybe you should check the values of the temperatures you are putting. You should use actual temperature, right? Okay, so here I'll probably expand the formula, which will be Cp into T03 minus T04 minus Cp into T02 minus T01. So Cp is anyways 1005. What is T03? What did we find out? T03 is 1210 Kelvin. That was given. Okay, so this is 1210 minus T04, which is 886. Then minus T02, which is 463 Kelvin. And then minus becomes plus T01, and that is given to be 298. So is this what you are doing? What is the answer that you are getting? Hello, am I audible still? Yeah, right. Now it's right. It's 159.79 kilojoule per kg. Yes. Which is okay. Yeah. So see, this is the mistake. You shouldn't take T04S. So when you are calculating the work of turbine or of compressor, you should take the value which is which you have got in actual. So these values, these are only to help you for calculation, and this path that we assume, that is the ideal isentropic path, that is not the reality. Reality is along this non-isentropic path. So the values that you use in calculating work or heat output, input, that should be the actual conditions, actual temperature, actual pressure. Okay. Okay, so now what is the last part is thermal efficiency. What is thermal efficiency? So here you are basically changing the kinetic energy, or you're giving some net work in. That is nothing but work of turbine minus work of compressor, which we calculated. divided by the total heat input that is there. Okay, so we can find the total heat input. What is total heat input? It will be Cp times T03 minus T02, right? So use this and tell me what is the thermal efficiency. No, work net is we have already calculated that is 159.79. No, that's not the answer that I have. Again, anyone else? Anyone else has any other answer? So what is T03 that you will put here? 1210 Kelvin minus T02. So go back, T02 is 463, right? So what is the answer going to be? Yeah, it's 21. So it's approximately 21%. Okay, so thermal efficiency is around 21%. So these are the answers. Yeah. Yeah, the one we used earlier, that we used in the previous question. So you use that formula, is it? Okay, so so the question here is, she calculated the thermal efficiency using the formula that we used in our previous question. That is, this thermal efficiency is 1 minus 1 by the pressure ratio to the power gamma minus 1 by gamma. Can we use this in this particular question? Can we use this formula? Yeah. So can we use? Think and tell me. Can we use it, or if we can, why can we use this? How was the derivation done? If we cannot, why we cannot use it? Yeah, so exactly. So when you did the derivation of that particular formula, you used an ideal cycle, right? And whatever is given in this question, I told you have to use the real values. So during the derivation of that formula, where you have the relation between the thermal efficiency 1 minus 1 by the pressure ratio to the power gamma minus 1 by gamma, I also told you the derivation comes from. So remember, the first step of the derivation that we wrote is H03 minus H04 minus H02 minus H01. These values, these are the ideal values, right? But when we are calculating thermal efficiency for the next question, we have to use the real values. Then this derivation will not work. This formula cannot be used for the next question. In this question, everything is assumed to be ideal. There is no efficiency, component wise efficiency that is given. So you can use this formula. Okay. Okay, so we are way above time now. I'll stop recording. Are there any questions? Yeah. Which question is this? Can you tell me? Yeah. Okay, some other question. So you are saying. So you are saying that you have a particular question in which you have a compressor. You have a compressor, and then after the combustion chamber you have two turbines. Okay, so where this is, say, the high pressure turbine, and then you have a low pressure turbine. So the apart from compressor, you would also be having some fan or shaft or something, right? Because high pressure turbine will be running the compressor, right? So you'll say that work out due to the high pressure turbine is being used as work input to the compressor. Okay. Similarly, work output from your lower pressure turbine will be used as work input to say for example this is a turbofan, then maybe it is being used to run the fan, or it could be a shaft in the case of a turbo propeller. So that would be given in the question, and then using this uh, relation you can find the relation between the T knots. So let us say this was T naught 2, T naught 3, this is T naught 4 and T naught 5, and this is T naught 6. So in the high pressure turbine it will be T naught 5 minus T naught 4, right? And in the low pressure turbine it will be T naught 6 minus T naught 5. So that you have to use over here. Okay, and from that say this was again ideal, then you can find the pressure ratios using the adiabatic relations. Otherwise then they will give a efficiency per turbine, efficiency of the high pressure turbine, efficiency of the low pressure turbine, and then you can calculate like we did in the last question. Okay. Okay, so I'll stop recording, but I'll stay if there are more questions I'll just stay back.